Hello, and welcome to this overview of advanced AI-assisted tools and methods for improving equipment reliability. So the goal is to eliminate manufacturing equipment failures and the resulting downtime and yield loss, while also eliminating or minimizing predictive monitoring and eliminating or minimizing all types of maintenance. A few examples. In one case where we had an ongoing problem where it seemed to be a necessary trade-off between process and safety, and of course safety always won in that trade-off, but we needed process capability as well. To that point, only had a couple ideas, but within about a 3-week period, we had generated a great number of ideas. You can see the ones in blue that were evaluated by the customer as much more effective than what they had developed using these methods. Another one was a litho materials problem. After 3 years, the supplier and client team had hit a dead end. Their design of experiments were inconclusive, multiple failed solutions, and they needed we accomplished the clarity of the problem to be greatly increased. We also developed an in-depth fundamental model of how they functioned, and ended up with 21 concepts generated and documented. 6 of them were deemed by the customer to be highly effective and low complexity to implement, with 4 of them being patentable concepts. Another one where a factory manager was very skeptical about this approach. They had dealt with this problem for a few years. They had developed many solutions over that period. You can see there's maybe 10 or 12 over, again, several years. They gave us 1 day to address this. And within that 1 day, we developed about 50% more than what they had come up with, and some of them slightly better than any of their solutions. Another one with CVD yield loss. There was one component suspected to be the culprit. This failure caused yield loss and required part replacement and lengthy cleans. We needed to enforce the collection of more specific data, document each failure mode instead of just the general failure. We needed to know the number of wafers from installation to each and every failure mode occurrence. And we also include data from tools that had not seen that failure during any given time period, we needed to know the number of wafers since the last replacement. And 3 different specific modes were identified, and we plotted each of those failure modes on a special Weibull paper. The most frequent mode was clearly an infant mortality mode. We'll explain more about that later. Typical causes for infant mortality are often poor quality, inconsistency in operation, environment, and installation. As part of the investigation, the techs were questioned on how they perform a replacement. The finding was that only some of the techs use a torque wrench during one of the steps. Maintenance tasks were clarified, standardized, which resulted in the elimination of that failure mode because it was essential to use a torque wrench. For the other failure modes, they now knew the probability of occurrence after any number of wafers, which could be used to consider monitoring strategies or scheduled replacement or other maintenance. There are maturity levels, generally speaking, that we look at. One is, at first, a factory will prioritize output over maintenance. This ends up being resulting in excessive unscheduled downtime and yield loss. The next step is do any and all recommended maintenance tasks. So it's sort of responding with an extreme approach the opposite way. So do lots of maintenance. Then, of course, the unscheduled downtime gets better, but the output is limited by all of that scheduled maintenance. The next step might be the emphasis on predictive monitoring. And there's nothing wrong with that, by the way. And then the fourth would be perform the right maintenance at the right frequency, minimize unscheduled downtime, while also minimizing the amount of maintenance and only doing the monitoring where necessary. So a high-level overview of this process would be we need to go from failures to failure modes, the ways in which something fails. We go from MTBF, or mean wafers between failure, to using something like the Weibull distribution to understand probabilities of failure instead of averages. We needed to, or this helps us to understand the nature of each failure mode as well. For instance, whether it is an example of infant mortality, wear out, or random occurrences. We also go from relying upon brainstorming and expert opinion to using rigorous physics-based causal analysis to identify, for instance, what to monitor. Then finally, we go from assuming that you can eliminate a failure to identifying several elegant solution paths, or having the confidence that you can do that, which eliminate the failure while also reducing monitoring and reducing maintenance to what's absolutely necessary. So as far as moving from failures to failure modes, an example might be tracking the frequency of tire blowouts. To get down to modes, we might say we need to track the common, easily identifiable ways that a blowout occurs, low tire pressure, small punctures, or large damage from road hazards, and so on. Some of those causes are already monitored, like the low tire pressure. Others could be monitored. Others seem impossible to monitor. Good data on all these things is limited. When it comes to MTBF or MWBF, really don't like that metric. Averages are weak. We don't have a confidence level. There's not much insight, and they can be misleading. In these four cases, let's say these four are all different tools, the same type of tool. And these are histograms or frequency distributions. And you can see case number 1 looks very different from case number 2 and 3 and 4. However, it's interesting to note that all 4 of those have the same average, which, if that's all you looked at was averages, you wouldn't have a clue as to how different they were actually performing. There is a formula for giving you confidence levels on these, and as an example, too, of the misleading nature of averages. Of course, if you run a lot of wafers, 10,000, see 100 failures, you have a MWBF, or average, of 100. For number 2, if you ran 1,000 and had 10 failures, you also have a MWBF of 100. Number 3, run 100, have 1 failure, you also have a MWBF of 100. But when you consider a 90% confidence level on those, you can see they're much different. For running a lot of wafers, you're confident the MTBF or MWBF is 91 down to 33 for that last example. So, Weibull analysis. This is where we need to enforce the collection of more specific data, documenting each failure mode instead of just the failure, number of wafers from installation to each failure mode. We need to include tools that did not see a failure during that time period, the number of wafers run since the last replacement without requiring that replacement yet. We plot data for each of these failure modes on special Weibull paper, where the y-axis is the cumulative probability of failure, and the x-axis is a log scale used for time or wafer count at the occurrence of each failure mode. The slope of the line that fits the plotted data points that are put on there, if it fits the line nicely, it is considered to be represented by this distribution quite well. In this case, if the slope of the line is less than 1, that gives us a clear indication that we're looking at early failures or infant mortality. If there's a constant failure rate where the slope is equal to 1, the failure rate or the failures occur randomly, often the case with purely electronic components. And then finally, wear-out failures are ones where the slope is greater than 1, so it performs really well for a considerable period of time, and then it goes bad pretty quickly. There's also a significant item listed on here or shown on here. It's the plotted line where the plotted line crosses the 63.2% line is called the ADA, or characteristic life. A fun fact there as well is when you say that MWBF is 100 wafers, or there's 100 wafers between failure. That actually means that you're saying 63.2% of the time it'll fail before it ever gets to 100. And then you can read also the cumulative probability of failure at any time or number of wafers by looking at that y-axis again. This particular technique and many others we'll talk about are assisted by the artificial intelligence tools that we're working on, as well as other free tools. For common root cause analysis, things like root cause analysis, brainstorming, 5 whys, fishbones, and so on, they're suitable when the problem is common, well understood, the causes are known with high confidence, the effectiveness of solutions is well known, and everyone is happy with that particular method and the results. Potential deficiencies of these approaches are the quality of the analysis really depends on the group members, their experience, their group dynamics. If one expert dominates the discussion and only his or her opinion is respected. Proposed solutions are not necessarily tied back to causes. Often a single cause is assumed to exist. There's limited understanding really of the system or process. Limited number of opportunities for improvement are identified, and a limited number of solution options are generated. For determining input variables for design of experiments, as well as for predictive monitors, we want to avoid using consensus or judgments from experts. We want to be aware if we are monitoring something just because we can. In this case, I don't just want to look in where a street light is illuminating the ground to find the quarter that I dropped because the light is better there. We want to look everywhere or find what it is we really need. So we use something we call physics-based causal analysis, developed and tested within semiconductor, aerospace, and several other industries. The intention is not just to find a single cause. Instead, it seeks to uncover many knobs which could be turned in to eliminate the problem in the next step. So we're guided by physics or sciences instead of brainstorming. We want to model causes with equations. That's where we drive each level of a diagram. In this case, if we're talking about rear-end collisions. And if you don't feel confident at all that you know about the factors, these AI tools are going to help tremendously. For instance, we might start with braking distance, and we'd say it is a function of, and then there'd be some brainstorming. Well, it's speed, it's thinking time, coefficient of friction. We might even say it's the condition of the tires, or it's how well this person really knows how to drive. Then we have to look at these factors as they relate to each other. We need equations. with that. So as far as equations and knobs for this rear-end collisions problem, we can go back to a basic physics textbook and get some formulas that show what factors are part of those formulas, and those will be part of the equation, and we'll call them knobs. AI assisted again, luckily, in case you forgot your physics or you're not an expert in that area. So this process can be slow, and you may have to start over again and maybe again. But this just means that you're learning and you are willing to admit it, so you keep going. The goal is to make the diagram irrefutable and complete and void of opinion. So our first attempt at doing a causal analysis is shown here. And yes, we do it upside down to differentiate it from other forms. So down here we have car stopping distance capability is long. From that formula, we put up here the next level is coefficient of friction and speed. Nothing else at that level. Then we can also use what we can find in textbooks or by using AI. What are the factors that go into the coefficient of friction, being a friction coupling, tread condition, road condition, and so on. Then a second attempt, we realized that while we looked at the stopping capability of the car, it's more important to consider the bigger picture, which is the ability of the driver to stop the car before hitting the lead car. So we've redefined this. We've added this down here. Stopping distance is long, and there's the stopping distance capability. But then we start to add things like the time to think or interpret what we are seeing. The time to do that is long. And then once we understand it, the time it takes to react appropriately is long, or I should say the distance is long. From each of those, we can start to go deeper. There's where we looked at before, coefficient of friction and so on. But now we're going to go into thinking time and reaction time, which could be labeled differently. But again, using AI tools, you can get a good head start and have it make sense to you. Now we step back even further to consider why a driver may be driving at an unsafe speed and why the distance to the lead car is small. In other words, you can do all you want technically to a car or to the thinking about the human factors and their ability to react. But then the other side is the motivation, emotion, and behavior. So the things like the belief that the lead car won't slow down, or the belief that my car can stop very quickly, and then resulting things from there, or things that feed into that, like the awareness of the distance is slow. It could be different forms of cognitive bias and emotion that drives that. And again, AI assistance, luckily, is there. So why consider human motivation and behavior? Well, once at a semiconductor manufacturing facility, a small group of techs shared that it was not really in their financial interest to work on eliminating failures. That's because they realize they earn a lot of money through overtime when their workload increases or continues to respond to those failures and the very lengthy maintenance. Then in a power generation plant where temperatures outside could get lower than 20 degrees below 0 Fahrenheit, it happened that the junior, inexperienced technicians were required to spend more time doing outside maintenance. So you didn't have the most knowledgeable people performing those particular tasks. Here's another simple example. Let's say you are pounding piles, wooden piles, into the ocean floor that are going to support a small building or a dock. Problem is it takes too long to pound one in, and that means higher cost. We have to rent the equipment for longer. We have to have the people that'll do it for longer, and it delays the whole project. Now, to get started, as often happens, it's good. They question everything they know. And they tried asking Google how to speed up pounding of a pile into the ocean floor. How many? 7,920,000 results. So now you've got to dig through all these, try to find ones that are going to really give you what you think you're looking for. However, with the AI assistants I've been talking about, you essentially can ask your initial question and then lots of follow-up questions, and ask them as if you're talking to an expert or a friend, or ideally a friendly expert. Think of AI as a friendly expert, though definitely not infallible. So you can ask questions like, why does it take so long? What factors determine the time? Is there a formula? Describe the factors and forces. What are the two types of forces that determine the rate of penetration? Are there other resistive forces? And so on. So with causal analysis, again, we're going to use what we've learned so far and then add our judgment on the basic level. You use the formula for what determines time. So time in this case, to pound it in, is just distance divided by speed. So the required depth that I need to pound it and how long, or I'm sorry, the speed at which it can be pounded in. AI helps. The next would be, we know that the speed is actually a rate. It is a function of the distance driven per strike and the time for each strike cycle. AI helps again. Now we can look at the fact that we know that the distance driven with each strike will have two forces. So there's the distance driven. I'll add driving forces at the end of the pile are small, and resistive forces are large. Pretty basic. Again, if that isn't basic to you, AI can help. These are the basic types of resistive forces. Something called a skin friction is high on the sides of the pile, and the end-bearing resistance is high. The AI-assisted tools that we have available definitely assist with that. There are many parts that have not been expanded upon. However, we have already identified several opportunities to make a huge improvement. In this case, we can see for that end-bearing resistance is high. We would say there are basically two elements to that. One is the soil condition, and the other is the diameter of the pile. So if there's a smaller diameter, it may go in faster. And again, to know what that is, you can ask questions of different AI models and get that very efficiently. So contradictions are really opportunities. You can identify many extreme conditions which resolved would be revolutionary. You might ask for the time to pound in a pile. Yes, the required driving distance is long. What if I could make it? That's what the green one represents. What if I made a contradiction that said, no, I really want it short. However, if I make it really short distance, perhaps the stability would be low. So I want it to take a long time so that stability is greater, but I want the distance to be short so the time to go in is shorter. So could I get the required depth to be shallow and deep with nothing in between? I know that sounds crazy. In this case, again, speed or velocity is low. What if I made it fast? Well, is it able to, and would there be damage to the pile or the pile driving equipment? So we want to continue defining contradictions all through this tree. With each one, we identify the potential downside to changing the factor to its opposite condition. So in this case, for speed or velocity is low, we have distance driven is short, and the time for each cycle is long. With the distance driven per strike being short, what if we could change it to the distance driven per strike is long? That would be good as far as speed. However, what would there be that's negative about that? Perhaps it would be such a hard strike that you might break the pile sometime, maybe other things. Over on this side, time for each strike cycle is long. What if you could make that very short? What could be negative about a very short cycle? Would be that it could be once you drive it in, it might continue to sink over time. So I'd like to have large resistive forces and small, and not something in between. Another one would be pile tip diameter is large, pile tip diameter is small. You could also interpret that as a flat bottom pile or a pointed pile. There would be the pile tip diameter is small would help to reduce the resistance. However, the downside again would be that it would possibly go lower. So we'll stop right there, pick the tip of the pile to look at. Again, why would you want it to be large? Why would you want it to be small? It seems crazy. I would like the point to be sharp, and I would like it to be flat, and I also don't want anything in between. We might commonly think about optimizing or figuring out a trade-off, or what would be the best amount of a point or pointiness that we would want to achieve. If the pile becomes more sharp, that could hurt the stability. It could sink further. And also, as the sharpness increases, the driving speed does get better. And you could figure out the optimum sharpness, but that is not a very elegant, good solution. So then the systematic generation of solutions using trees. If you haven't heard of trees yet, you'll want to explore that a little bit. And specifically, we look at a series of books and a website at opensourcetrees.com. The books are referred to as Trees Power Tools. I'm a co-author of that series along with the main author, Larry Ball. So regarding trees, there are thousands of examples of how seemingly impossible contradictions have been completely resolved. Fortunately, the design strategies that were used in each of those cases have been cataloged, and it turns out there are only 9 separation strategies, or way to make something large and small, hard and soft, and so on. So 9 strategies and perhaps 50 or so specific methods to accomplish those. The goal again is elegant solutions, ones that are simple, inexpensive or free, and without compromises or trade-offs. An example of one of these strategies is separate in time. So you ask, under what conditions must those 2 properties exist? In this case, if it were possible to do, if you rearrange something about the tip such that when it goes in, it's sharp, and then after it's in, it takes a more flat shape. Don't know exactly how that would be done, but that's the concept to evaluate. Another one is sort of similar to that. So you pound it in as a sharp pile, perhaps explode or segment the tip of that pile, and now it's essentially flat. Another one is nesting, where you could arrange individual small piles, very thin, which go in easily, and use a shaping cap where all of those piles are nested within one element, and that is what gets pounded in. After it is in, remove the cap and continue pounding in the rest. Transformable states, what if you could make the tip of the pile of some sort of abradable material such that now when you have it into the desired depth, that point is gone. Another one is copy. Drive in a sharp copy of a pile, remove that, and drive in a blunt pile. Now it's both sharp and it's blunt. We separated those things in time, just like the rest of these. There's prior counteraction. If we pounded sharp piles in at opposing angles, they would work against each other and provide, again, the benefit of sharp and the benefit of a flat bottom pile. Then a variation on separate in time is separate gradually. We could take individual sharp piles, pound them in, very easy to pound in because they have a small diameter. And once you get them all pounded in and perhaps bind them together, now it essentially has a flat bottom. And again, coming up with these ideas, using those strategies, we are in the process of developing AI tools to enable that. Another method is separate in space. Is it possible to put the different properties at the same time in different areas? One is you use two objects, whatever it is. You could put in a sharp pile and right next to it a flat pile. So again, you get the benefit of both the stability of the flat pile and you get the depth that you need from the pointed pile. Here again, you could, a variation on that, you could attach them. So the sharp one goes in well, you attach a flat bottom pile to it and don't need to really pound it in any further. You have the benefit of both. Another one would be that the sharp pile has a way of driving the flat bottom pile, so it's nested within, and again, you get the benefit of both. You could make the bottom of the pile non-uniform, where the edges of it are flat, the middle of it is sharp. Again, using these concepts or strategies, these AI tools will help you come up with specific solutions. So, a comment about monitoring. The common guidelines for choosing the right variables for monitoring would include things like defining the objective, understanding the domain, data collection, feature selection, dimensionality, and so on. However, up with number 2, understand the domain, the directions often minimize the work associated with getting a deep understanding. What does that really mean? Is there a rigorous causal analysis model that could be developed? Well, there's rarely any mention of some kind of rigorous process. And then at the bottom, it is essential to choose variables that are not only relevant and important, but also available and easily collected in real time. Well, they're sort of releasing people of the obligation or the goal of don't just collect what is easily collectible. Focus on what is needed instead, even if it seems hard or impossible. Or the ultimate is analyze the failure more deeply and work to eliminate it. So, eliminating causes, problems, maintenance tasks. With the example we just covered, we looked at 11 design strategies, 11 design strategies using only 2 of the separation strategies in that case. And we came up with, or eventually we have come up with at least 25 approaches to eliminate this failure. So the summary of the intent of this, understand the nature of all specific failure modes. Use a physics-based causal analysis to be objective, thorough, rigorous, and don't have an assumption that there is a single root cause. Identify the limiting contradictions. The contradictions and how you approach those are key. The more stark or blunt contradiction, the more opportunity there is for a real breakthrough solution. And that's where TREES comes in to provide a systematic way of generating elegant solutions. So prioritization, eliminate the problem without extra maintenance or monitoring. If you need to, monitor the right things and maintain the right things at the right interval. However, for all these methods discussed, this is not for everyone. Actually, only a very few. It's very difficult to learn, takes a long time, and it's not for every problem, mostly for the most technical problems that could have a large payoff for the company. Again, this is not easy or quick to learn and apply. Sometimes it's messy. It takes persistence, determination, and even humility, admitting that you don't know everything and are open to what is uncovered. The student must be self-driven. If it's forced upon anyone, that they have to absorb something that they're really not that thrilled about, it's not going to happen. And these are not team exercises. You cannot set deadlines, even though the efficiency has been well documented for this approach. Leaders must believe in the investment and protect the practitioners because they're venturing into new categories. And lastly, need to document the financial payoff throughout the process to maintain support. So there is additional information and training like overviews, discussions with leaders, could be 2 to 4 hours, awareness/training for a larger group, with one of the goals being to see who would be interested in diving deeper. These training classes could last a day, perhaps. Then there are training workshops for the people who've decided they want to go deeply into this, which might be 3 to 5 days. There's the idea of doing a pilot project with at least one domain expert working with a consultant like us. And that might take 4 weeks, not full time, but it could take a while. And then there's individual coaching, mentoring to become self-sufficient. That could be 3 to 9 months, completely varies or depends on the situation. So, thanks for your time. This is longer than I wanted it to be. Hopefully it is of some use, and please contact us anytime for more information and to discuss possible next steps. Thanks.